Hello students, in this video we'll prove Euler's formula for the Riemann Zeta function. Let's recall the Riemann Zeta function we've been studying is the sum, n goes from 1 to infinity, of 1 over n to the z, right? And this is defined for all z whose real part is bigger than 0 and is a pole at z equals 1, right? Defined on the entire complex plane, except for 0 and 1. And it has simple poles at z equals 1 and 0. Excellent. And that, of course, follows from our discussion of the psi function, right? Our psi function over here is going to be what? Our psi function is going to be zeta of s, pi to the negative s over 2, and then gamma of s over 2. That's our xc function, and we know that this has symmetry, right? We know that we know that this is equal to xc of 1 minus s, and that gives us the structure of where the poles of the zeta function are, right? There's a pole at 1, so there has to be a pole at 0, right? So this implies the pole at 1 gives a pole at 0. Okay, so there are two poles of the Riemann Zeta function. We're going to analyze the pole at z equals 1 carefully in this by using Euler's formula. So what does Euler's formula tell us? So here's the proposition, here's the theorem due to Euler. Okay, it says zeta of z is really the product over p prime of 1 what? Of 1 over 1 minus p to the negative s, like that, or z in this case. So let me z over there. Negative z. Okay. And so how do we prove this result? So we have to recall the fundamental theorem of algebra. Very simple thing. Recall the fundamental theorem of algebra of arithmetic, rather. Says that any natural number n can be written as p1 to the k1, pl to the kl, product of primes to different powers, right? Okay, excellent. And so here's what we're going to do. We're going to fix two natural numbers. So let m and n be an n, with m bigger than n, like so, okay? Then what can we say? If I look at the truncation of zeta up to n, then the sum j goes from 1 up to n capital of 1 over j to the z is less than or equal to what? Is less than or equal to the product over all primes less than or equal to n, p prime, p less than or equal to n, and then what? And then 1 over, I'm just expanding this out in a geometric progression over here, right? So I expand this out in a geometric progression, what will I get? I'll get what? I'll get a 1. So we're going to start with a 1. And then plus 1 over p to the what? P to the z, plus 1 over p to the z squared, 2z, etc., all the way down to what? 1 over p to the m. I'll stop it at mz, right? Like so. Okay, now let's figure out why this is true, right? Well, let's think about what would happen. How would I get a 1? I would get a 1 by multiplying all the 1s in this expansion over here. Good, now I get 1 for free. Okay, how do I get 1 over 2 to the z? Well, 2 is a prime, right? If 2 is less than n, then 2 is going to occur at 1 over 2 to the z. We would get it, right? If n was 3, I'd have 1 over 3 to the z, right? Well, 3 would be a prime less than n, so I get a 1 over 3 to the z. Here comes the tricky part. What happens when if n was equal to 4? Then I have a 1 over 4 to the z in this sum, right? Where does the 4 appear? The 4 appears right over here, right? Because I have a 1 over 2 squared z, which is going to be a 4 to the z. And I know that, of course, that m is bigger than n, so I know I have to at least get that number in there. So m is bigger than n ensures that I get that 4. 5 and 6 follow the same reasoning. 6 I'll get from what? From the 2 over here, from p equals 2, and the p equals 3 is in the next term, et cetera, et cetera, et cetera. How do I get to 8? I get to 8 by doing the what? Go down to the third thing over here because I know that's m. If n was equal to 8, I know that m is bigger than 8, so I definitely get a what? I definitely get a 2 to the 8z, so I mean I definitely get an 8 to the power z. So this inequality is true by the fundamental theorem of arithmetic. Now I'm going to let m and n go to infinity, so as m and n go to infinity, what can we conclude from this? We can conclude as m goes to infinity, as n goes to infinity, that the sum, j, goes from 1 to infinity of 1 over j to the z is less than or equal to the product p prime 1 over 1 minus p to the negative z, like that. Beautiful. So we have that inequality for free. We get that inequality from this estimate. And then similarly, I know that if I look at the product p prime, p less than or equal to n, and then I look at this truncation, this geometric progression over here, 1 plus 1 over p to the z all the way to 1 over p to the m z, that's less than or equal to, that's all of the what? That's all of these numbers over here. But I'm missing some of them, right? I'm missing some of the ones that are higher than all the powers of what? The highest power, I'm missing the next prime, basically, right? The next prime does not appear in this list, so therefore I cannot get all of the terms in my series that look like this. So in other words, the infinite series contains all of these expressions and more, right? Now I let m and n go to infinity, right? And conclude that the product p prime 1 over 1 minus p to the negative z is less than or equal to the sum, n goes from 1 to infinity, of 1 over n to the z, which is just zeta of z. So we've just proven, of course, that zeta of z is what? Zeta of z is less than, that's of course zeta of z. Zeta of z is less than or equal to this, and it's greater than or equal to this. Therefore, it has to be equal to this product over here. Now, this gives us some nice, this is a really nice expression over here. So now I get one immediate consequence of this. What's one corollary of this? We had a beautiful corollary, which is hard to prove without use of this theorem over here. And now if I plug in zeta of 1, we know that zeta of 1 is infinity, right? It's a pole. Okay? But what would zeta of 1 be? Zeta of 1 is really what? Zeta of 1 is really the product p prime 1 over 1 minus p, right? To the negative 1. Well, what does that tell you about the sum of the reciprocals of primes, right? It tells you that 1 over the sum of the reciprocals of primes has to be divergent, right? So if I sum over p prime 1 over p, that has to be infinity, right? In fact, it's going to grow like log, right? And so we can show that in a further video that it's really growing like log, but we've actually just classified the structure, the rate of growth over here. So this product over here is going to be divergent to the negative 1, of course, right? To the negative 1. So that proves, of course, that when you rationalize this, that's going to show that 1 over p is going to be divergent, because I can compare this, of course, with what? I can compare this with the series 1 over p. So in other words, that product's going to converge if and only if this product converges. Since I know that this product diverges, I know the sum has to diverge. So I know that the sum of the reciprocals of the primes is at a divergent series, which shows that even though they're sort of spaced out pretty far, it's enough to show that they still diverge, which is a remarkable theorem, because we know that that's tightly related to the sum of squares, right? So in other words, we want to compare those two series in further videos and see how they connect. Thank you very much.